Hey guys, welcome to my introductory video on how to find the area under the curve. This is going to introduce the idea of essentially what's going to be known as integration in calculus, and we're going to be looking at it with a method known as Riemann sums in this video. So what you're seeing first, especially for those of you that are following along with the notes associated with this course, is the idea of so far what we've been talking about up to this point has been in some ways the derivative of a function which was based on the idea of a limit. Well, we can kind of take the same approach with the area under a curve, and that's what we're going to be looking at for integration. Now, we're going to start it off with something very simple, just some basic rectangles and at some point some trapezoids. So the idea here that we're talking about, what I want to highlight here is this bit here. The second classical kind of problem in calculus is the area problem, finding the area under the curve, specifically the part that's bounded by something under the graph. Okay, so kind of what that's going to look like, imagine you have some function, whatever that function happens to be, okay? If I pick a point here and a point here, the area that we're going to be looking at is all of this stuff. That's what we're going to be looking to try and identify. That's why they're saying we're going to have those two x values, and it's just going to be the area bounded between the x-axis and whatever the curve happens to be. Now, here I drew it as something that was going to be above the x-axis, which of course would represent a positive area or a positive distance maybe. But if we went below the x-axis, that would represent something negative. So here is a classic kind of way of looking at it. Again, we use limits to establish how we can identify the instantaneous rate of change in order to identify the derivatives of functions. Well, here we're going to be looking at it in terms of, and what they're showing you in quotes is the limit of rectangles. So imagine that we have some function, and the example that I've selected for you here is kind of a typical sinusoidal curve. And you can see on the left-hand side, the part that's above the horizontal line, we have a handful of rectangles where the bases are, whatever length that they happen to be. Well, if we start increasing those rectangles without limit to where I have an infinite number of rectangles, and you can kind of see on the right for the part of the curve that's underneath the horizontal line, the number of rectangles is increased quite a bit. Now this would be representing like sample rate. So if you were trying to recreate something digitally, this is how CDs and digital music originally was done. They would take an audio recording, which is of course, done analog, back in the day, and they would take sample rates of that analog signal to try and recreate it digitally. And the more, or the higher the sample rate, the more true the reproduction would be to the original. So the higher the sample rate, the more accurate the signal, the more accurate something is going to be. And in this case, if we increase the sample rate or the number of rectangles underneath the curve, then or if we increase that to infinity, then that essentially is going to get us the area, the exact area underneath the curve, and that is what we're thinking of as integration in calculus. So, like I said, we're going to be looking at something known as Riemann sums. Now, to start off with, we're going to be kind of keeping things simple here. Everything's going to be positive. Everything's going to be above the x-axis. And we're going to be approximating areas using rectangles, and this is known as Riemann sums. There are three types of Riemann sums. There's a left-hand Riemann sum, a right-hand Riemann sum, and a midpoint Riemann sum. So the left-hand rule says that the left corner of the rectangle must be touching whatever the curve happens to be. In this case, we just have a line. So the left-hand corner of each rectangle is the only part that's going to come in contact with the curve. Now, of course, here you can see that the height of the rectangle at the very beginning is 0. So the way that I would approximate the curve is just with the sum of those 3 rectangles. Now, for a right-hand Riemann sum, you can see that the only point of each rectangle is going to be whatever or wherever the right uppermost corner of the rectangle is going to come in contact with your curve. So you can see both from what we've well, let me go ahead and look at this here, because one thing that I'm neglecting to mention is that the base of the rectangles, all of these bases, or I guess you could really think of it as, you know, the height of the rectangle. It doesn't really make a difference, base or height. These are all congruent. So whatever they, you know, if let's just say that this is x, this is x, this is x, they're all the same length. That's kind of important when we're looking at a Riemann sum. But you can kind of see very clearly with all of this bit that's above the line, in this case above the curve, that we're going to wind up with more this is what we'd be looking at as an overestimate, where what we saw previously with the left hand stuff, you see all of this, you know, blank white stuff here, that's missing from the area underneath the curve. So this would be considered an underestimate for this example. We'll talk about that more in a little bit. So here, this is the midpoint one, and that means that the middle of the base of the rectangle is what's going to come in contact with the curve, whatever that happens to be. And in my experience, this is the one that kids kind of struggle with the most when they're having to, especially if they have to draw it, because I don't know, just something about the left corner and the right corner makes a lot of sense, but doing it from the middle, the midpoint of that base segment, for some reason seems to throw kids off. So pay particular attention when you're having to draw a midpoint rectangle for a Riemann sum. Here, this is where they're getting into kind of the mathy definition of what the definite integral definition is. Now, here when we're talking about definite integral, we're referring to the fact that we have a starting point and we have an ending point. We know we're going to start at some point on the x-axis and finish at some point on the x-axis. That's why they're giving us this kind of closed interval to work with here. Okay. Now, where it says, let the interval from A to B be partitioned into n subintervals. Well, these n subintervals, in this case, those are the rectangles that we're using for our Riemann sum. And this is what I was alluding to earlier, a moment ago, is that they have to be equal length, meaning that's like the base of the rectangle. The equal length, that's the base of the rectangles that we had. So from A to B, whatever that is, we're going to take the difference of them. So here, from B to A, these are your inputs. These are your x numbers. And the difference between them, that would just represent a horizontal distance. And n that we have here, this is the number of rectangles that we have. So that way, by taking whatever the horizontal distance is from point A to point B and dividing it by the number of rectangles that you're going to be using, that will ensure that delta x, in this case, is the going to be a consistently congruent base for each rectangle. And this, at the bottom, this is just representing that we're using a summation, where we're taking the sum of all of these rectangles And again, ideally, what we're going to be looking at or thinking about it is if the number of rectangles approaches infinity, that's how we're going to identify the exact area at some point as opposed to an approximate area. And this symbol here, this is actually called like a long S, like literally the letter S, like if it was stretched upwards like vertically like a rubber band. It's called a long S. That's the symbol that we use in calculus for integration, where A, this value, this is your lower bound, meaning your smaller x value, and this is your upper bound, meaning your larger x value. And I think that's all we needed here. So let's go ahead and start taking a look at them. So here, this in your notes, this is just talking about the actual process of what you're going to do. You have to draw in the rectangles. In some instances, those of you that are following along with your notes, you're going to need to be drawing in some rectangles here. You don't necessarily need to have a straight edge or anything to do it, but just understand that's what we're going to be doing. And of course, part 3, compute the x-coordinates of the rectangles at either the left end or the right end, because that's going to be important, knowing what those x values are going to be, because that essentially tells you where you're starting for your Riemann sum. The areas, in order to find the areas, we have to have the height of each one. So whatever the x values are, we're probably going to have to take those and substitute them into the given function, so that way we can actually know what the height of the rectangle would be at that particular point. And then once I have the area of all the rectangles, we just add them together. Now we're going to try and streamline it a little bit, obviously, but here's our first example. This is a very simple function to work with. There's really no calculus strictly needed in any way, but this is meant to kind of get you into the shallow end of the integration pool with our Riemann sums. So we're going to think of the line, even though it's a line, we're going to think of it as a curve. We're looking for the area under the curve. We're looking for the left-hand rule is what we're looking at according to the problem, and it's telling us that the interval, this is our A value, this is our B value, and it's telling us that we want 5 subintervals. So that's why the picture, the way it's been described, has been drawn with 5 rectangles underneath it. Okay, and of course, pay attention, we're only intersecting the curve with our rectangles with the left uppermost corner of each one. And so what we're going to do here, the easiest way of thinking about it is we want to identify a table of values. Okay, starting with, in this case, x is equal to 0. Substituting that into the function gives me an output of 1. Substituting x is equal to 1 for that kind of light bluish, I guess, color rectangle. When we substitute 1 in there, we get an output of 1.5. For the green rectangle, we substitute a 2, giving us a 2, and so on. So what we're looking at here is that all of these values here, these represent the heights of each rectangle. Now, what we're doing is we're taking from A to B and we're subtracting those from each other. So in this case, it's just 5 minus 0, but then we're dividing it by the number of intervals that we had, which in this case is 5. That's why the base of each rectangle happens to be 1. And we're trying to keep it simple like that for this example, because what we're going to do is we're showing here this bit is what we were thinking of as your delta x, the change in x. And it should be constant all the time. Okay, they should be the same value. That's why it's kind of factored outside of the parentheses. Because we know that the area of a rectangle is the base of the rectangle times the height of the rectangle, or length times width, however you want to think of it. So this is the base. Being common, it's been factored out of the equation of base times height, and all of these represent the heights of each individual rectangle that we're taking the sum of. So here in this case, the upper bound minus the lower bound gives us 5 minus 0. The 5 in the denominator came from the problem itself, saying that we're using 5 subintervals. The number of intervals could be anything, but we're keeping it simple with 5. We're taking the outputs from those left-hand corners, and we're substituting them into the function. And here, this is kind of a, I think I recognize this typo here. This should be 4 in this case because we don't actually use the input value of 5. Yeah, so that 3.5 didn't get used. And so we're going to just, take use our calculator, or do it in our head or whatever we want to, and take the sum of the stuff inside of the parentheses. We can see the division on the left side of the problem. The left side of the parentheses, that just simplifies to be 1, which again we kind of get that from the just looking at the graph. That's real easy to see. The base of each rectangle is 1. So in this case, the approximated area under the curve is 10 square units. Now clearly we have all of this, white space here. Let me pick a different color so that way the red and stuff doesn't keep blending together. Let's try this color here. So all of this white space should be considered part of the area under the curve, but of course it's not accounted for using this method. That's why we would say that the area in this case is considered an underestimate. Now for a right-hand Riemann sum, they're changing up the type of function that we're working with here. They're giving us part of a quadratic over the interval from 0 to 2, and we want to find the approximated area under the curve here. So the first thing you need to do, if you notice, the rectangles are not given to you. So you need to try to draw the rectangles in. So go ahead and pause the video and try and draw the rectangles in using right-hand Riemann sums. And when you're ready, hit play and see what mine look like. So presuming that you've done that, here, this is what my right-hand Riemann sums look like. Remember, only the uppermost right corner of each rectangle will come in contact with the curve. So here, again, they're identifying the interval that we're looking at from 0 to 2. They're telling us again that we're using 5 subintervals. And so you can kind of see in the picture that was here that each base is just 4/10 of a unit. Okay, so we don't really need to do the whole b minus a divided by 2 thing, but we'll go ahead and stick with it to keep things consistent. Now the heights, again, the heights that we're seeing, excuse me, that came out of nowhere. The heights that we're seeing in the table that I have are coming from me taking the input values and plugging them into the function. Now in this case, if you notice, the right-hand rule starts when x is equal to 0.4. So this value of 0 won't get included in our approximated area. And that's kind of the difference. That's one of the differences between left-hand rules and right-hand rules with Riemann sums, is essentially just where you start counting with your x values. So here we start with the input value of 0.4 because that is the first point where we actually come in contact with the x-axis, or I'm sorry, not with the x-axis, but with the curve, is when x is equal to 0.4. So that's why I'm starting with 0.4 here for my inputs. Now I probably should have just put the 2 minus 0 here divided by 5, but I think I have it written or typed in the next bit. So 2 minus 0 divided by 5, of course, is going to give me a base for each rectangle of 0.4. We take the output values that we got by substituting each particular number into the given quadratic function. And here, I would really just be doing this stuff with a scientific calculator or something. I'm not going to try and do all this stuff in my head, particularly because of the weird decimals. And when I am done, I'm going to have an area of almost 6.5, so 6.48 square units for the area. Now in this case again, based on the curve of the graph, you can see all those blank white triangles underneath the curve. This would also be considered an underestimate for the overall area. Now this is the one where students again are going to struggle a little bit because here it's telling you to use the midpoint Riemann sum. Okay, so they're giving us our interval from 0 to 3, and they're telling us how many rectangles that we need. So you can see very quickly that the base of each rectangle should just be 1/2, because we're going to say 3 minus 0 divided by 6, that's going to be 1/2. So what I want you to do, based on what the curve is to try drawing in the actual graph of the function. I'm sorry, not the graph of the function, but the rectangles for the midpoints, remembering that only the midpoint of the base will come in contact with the curve, or that's the only point that we really care about. So go ahead and pause the video, try drawing in your midpoint rectangles, and when you're done, hit play and see how I have it displayed. So presuming that you're doing, oops, what I'm asking you to do here, I don't have this one. There we go. This is what our midpoint rectangles are going to look like here. So if you notice, the way the horizontal x-axis has been done is that they're already kind of showing you that the base of each rectangle is 1/2. Okay, and so the midpoint of 1/2 is going to be right here at 1/4, and so that's the midpoint that I could use to come up, and that's where I draw my horizontal line for the other side of the rectangle. And I do the same thing again. Between the 1/2 here and the 1 here, I go to the 1.5, and that's the point that comes in contact that we care about for the height of our midpoint rectangles. Now I'm going to do the same thing here that I've done in the other two examples, is I'm going to just have a little table based off of the input function that we have, or based on the function that we have. So our quadratic function, ooh, come on, give me my computer is being possessed right now apparently. There we go. So the midpoints of each rectangle are things that we need to be able to identify correctly. So here are the midpoints of each rectangle that we're using. And of course, we plug those into the quadratic that we have, so that way we can get our corresponding heights, which are the decimal numbers under the y column of the x-axis, or the table. So, oops. So we follow the same process, and if you excuse my laziness, I didn't write every input in, or for my height, the stuff into the parentheses. I didn't type every single one because I just didn't have enough space for all of them. So here, the sum of all of the midpoint rectangles, starting from the 0.25 to the 2.75, or 0.25 to the 2.75, is 18. And I think that's an eighth, 0.125. And so we're going to multiply that by 1/2, and we get an approximated area of 9.0625 square units. Now here, what it's showing you is that drawing the rectangle isn't really necessary, although the graph, or drawing the function isn't really necessary, although I think it's helpful when you have it to use it. And sometimes even if you don't have it, I really do kind of like having the function drawn for me so I can kind of visualize it. But that's kind of a personal preference for me. The more rectangles you have, the more work you're going to have, but it'll give you a better area, a better approximation. But usually with Riemann sums, they tell you the number of rectangles that you're going to have, the number of subdivisions you're going to have. Because the base is the same, you can factor it out each time. And the only difference between the left and right hand Riemann sums is the first and last heights that are being used. Now here, it's asking you to just kind of give a condensed idea, a summary, I guess, that's the word I'm looking for, of whether based on the type of function that you have, being concave up, concave down, and whether that function is increasing or decreasing, are you going to have an over or an underestimate? Okay, so here I've added some images to kind of help us understand what that's going to be looking like. So on the left side of the screen, what you're seeing are concave up and concave down functions, but they're increasing, showing you when you're going to have under or over estimates. Same thing on the right hand side. They're concave up or concave down based off, but they're also decreasing functions, again, to show you an idea of when you're going to have something that's going to be either an overestimate or an underestimate. So here we're going to just be able to take visually what we see and identify when they're going to be an overestimate or an underestimate. And that's something that you can sketch for basically any problem that you have, understanding what the shape of the curve is going to look like, where the rectangles are going to be placed. You can very quickly identify whether it's going to be an overestimate or an underestimate. Now here, this example number 5, this is where we're going back to the idea of things that we saw previously in differentiation with position, velocity, and acceleration. In this case, we're talking about velocity of a function of something moving, in this case a car, and it tells you that we're moving in feet per second. The interval is for 50 seconds. And what it's asking us to do, it says to use the right-hand Riemann sums, the left-hand Riemann sums, and as well as a midpoint Riemann sum and something that we haven't used yet, the trapezoid. Now the trapezoid is typically going to be, if you're just getting an estimate using a geometric shape, usually the trapezoid is going to give you the most appropriate approximation. It's going to be the closest to the actual area. But let's take a look here. So we have the table that they're providing for us, and all we're going to do is we're going to take those data points and we're going to graph them. Okay, so take those data points, and what I want you to do, it says, go ahead and pause the video and see if you can work the whole problem out. Draw in your left-hand rectangles. Get it to where we have, what did we say? L5 with 5 partitions, so that's the number of rectangles that you're going to have, and see if you can approximate the area using the left-hand rule. So I'm presuming that you have tried working out the problem yourself. So here are my rectangles for the left-hand rule, of course, with the very beginning rectangle, because it's at the origin, the base or the height of the rectangle is going to be 0, so that's why we don't have a rectangle there. And the outputs, I'm just taking those from reading the graph and working it out. I get a base of each rectangle to be 10. The sum of the heights is 229. So that means the overall area, the distance traveled in this case, was 2,290 feet. Now again, the area of the rectangle would be, or the area of the approximation is the same, 2,290 units squared. But remember, if you're thinking about velocity, putting in terms of an application, if you take a speed and you go, you take some time and you take some speed, however much that speed is, even if you're just walking, that's going to translate into distance moved. And in this case, that's what it means. The area under the curve represents the distance that the car traveled over that time interval of 50 seconds. So here, same thing. I'm going to ask you to go ahead and pause the video and work this problem out. Same exact concept, except we're using the right-hand rule for Riemann sums. Still same number of intervals, 5 subintervals, and see what you get for your area. And when you're done, hit play, and hopefully your work and my work match. So here is the rectangles that I would have gotten for the right-hand Riemann sum. And again, I'm getting the same base of 10 units long for the rectangle. And now in this case, if you notice, the where we started for the sum of the heights is different than the left-hand rule was. So in this case, the sum of the heights is going to be 303, and that will translate when I multiply it by 10 into 3,030 feet traveled by the car in 50 seconds. And of course, you can see that's quite a bit different than what the left-hand rule was. But of course, generally speaking, this is going to be an overestimate. So here, this is the one that's going to be the most challenging, probably for students to draw. But again, I want you to try pausing the video and attempt answering this question on your own and see what you get. Now, presuming that you've done that, again, the first thing I'm going to want to do is draw in my rectangles. And here's what we have. So identifying, again, the heights from the table that we have, or from the graph that we have. Here, or I'm sorry, not the graph in this case, I'm really going back and referring to the table that we had. Looking at the heights, we have 14, 28, 70, 86, and 70 for the heights of each individual rectangle. And in this case, we're using 5 subintervals, so the base of the rectangles are still 10. And in this case, that translates into 2,680 feet traveled for the car in the 50 seconds. Now, the last thing that we're going to be taking a look at is something known as trapezoid. Now here, I don't anticipate you trying to pause the video and try and work this one out on your own. The trapezoid is going to be the trapezoid rule for a Riemann sum is going to be very similar to what we've done for left-hand or right-hand rules. We're still going to have the same horizontal length, but if you recall, here, I have some information here. You might want to make sure that you recall what it is. The area of a trapezoid in this case is half times the sum of the two bases times the height. Now in this case, the height of the trapezoid is actually going to be the horizontal distance. Your motion side to side on your x-axis. And the bases of your trapezoid, those are going to represent the heights, the two different heights that you have on the trapezoids when you draw them. So let's see. So here's the formula that we wind up working with. Okay, and it gets, if you want to copy it down, copy it down. You don't want to copy it down, that's fine too. But basically what we're doing is, because the height is the same for each rectangle, just like the base, trapezoid, just like the base was the same in each rectangle for the Riemann sum, that winds up getting factored out. But of course, if you notice, we're using, oops, didn't mean to do that. We're using a lot of the bases twice. So y1 gets used twice, y2 gets used twice, y3 gets used twice, and so on. So that's why they're all multiplied by 2 here. The only one that are not multiplied by 2 are the initial and the end. Okay? So that's how I'm getting that formula. But let's take a look at the triangle or at the trapezoids themselves and see what I have. So this is how I'm drawing my trapezoids. So again, the base of the trapezoid, the horizontal, I'm sorry, in this case, the height of the trapezoid, the horizontal, that's going to, what we were thinking of as the base of the rectangles earlier. That is the distance between the two bases, which in this case are actually the vertical segments. So this is how I'm drawing in the trapezoids here, where I'm taking the base and I'm kind of connecting the two dots of the heights. So hopefully, I know most of us from geometry, we're so kind of trained, I think, to think of trapezoids as being something like that. Uh, but in this case, we're kind of, this very much is a trapezoid also, where, we still have our parallel sides for our, that make the bases of the trapezoid, and this is going to be the height, okay? So that's how I'm drawing the trapezoids in. Now, based on that, we're going to say, okay, well, the height of the trapezoids, the horizontal distance, is still 10, just like it was with the rectangles. But according to the formula for every trapezoid, we multiply that by half, and then we take the sum of all of those heights that were being used. In this case, that's going to work out to be 532 times 5, which in this case works out to be about 2,660 feet traveled in the 50 seconds that it was being monitored. Okay, and this is, I believe, the last here. How does L5 find the average of L5 and R5, the left-hand rule and the right-hand rule, and compare that to the trapezoidal sum? So the sum of the left-hand rule and the right-hand rule were 29 or 2290 and 3030. Okay, so of course we're only adding those two numbers, so we divide it by 2, and that gives us the same value that the trapezoid rule gave us. And so that was the last kind of uh, connection that they're hoping that we can identify with Riemann sums. Now, I don't anticipate you really being asked that on an AP test at all. It, the only thing that I've ever seen for AP tests is just, could you do the Riemann sum, whether it was a left-hand rule, right-hand rule, or midpoint rule. Trapezoids, I don't think I've really seen too many of them as AP style questions, but as a geometric shape, the trapezoid approach generally gives us the closest approximation to the actual area than the rectangle is obviously going to be. But that should kind of wrap things up for this lesson. If I could, get my mouth to work properly. Thanks for watching, guys. I hope you learned something. And until next time, take care, be good, and we'll see you soon.